Okay, good afternoon, class. So today we will be talking about magnetic materials in this series of functional materials, whatever we have started. So today's lecture is going to cover the following topics. We'll talk a little bit about magnetic moments of electron and free atom. Then we will discuss, or I would say refresh your memory about the dia, para, ferro, ferri, and antiferromagnetism, what we mean by them. Then we'll talk a little bit about theories of paramagnetism and ordered magnetism. Then we will talk about hysteresis and related properties, magnetic anisotropy. Then we'll cover magnetostriction, magnetoresistance, magnetic domains, domain theory, magnetization processes in terms of domain theory. Then we'll cover application of magnetic materials, giant magnetoresistance materials and their applications. We'll touch upon ferroelectrics, ferroelectric RAM, that is random access memory. Then we'll talk about magnetoelectric effect, and we will sign off by discussing a little bit about multiferroic materials and their applications. So as you can see, the entire lecture is going to be devoted on all different kinds of magnetic materials and particularly magnetic phenomena. So before we actually move into all the material side and what are the different applications of it, refreshing your memories, what is the origin of magnetism? So it can be macroscopic, which is charge currents, and it can also be microscopic, which is the atomic scale. So we all know that if a loop of area A is carrying a current I, then the intrinsic intensity of the magnetic field is given by the magnetic moment vector m or mu, and it is directed from the north pole to the south pole, such that the magnitude of this m is given by m is equal to Ia. It's the product of the current and the area. And the magnetic moment is what? It is the measure of the strength of the magnet and is the ability to produce and be affected by a magnetic field. So what are the important quantities we'll be talking about when we talk all about this magnetic material? So these are few quantities which your memory needs to be refreshed. So we all have heard about the magnetic moment vector, which is m, and this is the measure of the strength of the magnet, and the unit is generally ampere meter square or joule per Tesla. Then you have the magnetic field strength or magnetizing force, which is given as H, and this is a measure of the strength of the externally applied field. Then you have magnetization, M, which is magnetic moment per unit volume. M is equal to mass by volume, and this M measures the material's response to the applied field H. And M is the magnetization which is induced by this applied external field H. So apart from this, we also have magnetic induction or magnetic flux density, which is given as B, and magnetic flux per unit area, we say, and the units are Tesla, which can be also written as Weber per meter square. So B is the magnetic flux density inside the material. So this B is nothing but mu0 H plus M, and mu0 is the magnetic permeability of vacuum. H I have already given. This is basically the applied field which you are applying, which is H, and M is the magnetization. And the unit for this is Webers per ampere per meter. Then you have something, a very important quality, which is known as permeability. And permeability is given as the ratio of B to H. And then you have magnetic susceptibility, which is the volume susceptibility. It's actually dimensionless, so it has no units. And this is given as chi, and this is nothing but magnetization over the external magnetic field, whatever you're applying. And this chi can be given expressed as mass susceptibility, or else it can also be expressed as molar susceptibility. And then you have energy of a magnetic moment, which is a scalar product of m into b. And another very important term which you should always remember is magnetic anisotropy. And this means that various directions in the crystal are non-equivalent with respect to magnetization. And this implies that M may not be the same in every direction of the applied field. So there are many contributions to this anisotropy, as we shall see later. Crystalline anisotropy being the most prominent one. Crystalline anisotropy is also known as magnetocrystalline anisotropy, and this is one of the most important contributions which we have when we talk about magnetic anisotropy. So now what is the response of a material to the magnetic field? So this is given as magnetization. M is the magnetization, H is the magnetic field. So magnetic susceptibility is delta M by delta H, and this actually is almost boils down to M by H. So what is the classification based on response to a magnetic field? It can be paramagnetic, so it is attracted by the magnetic field, or it can be diamagnetic, where it is kind of repelled by the magnetic field. So what are the sources of magnetism? As we have said that we have seen the charges in motion, as in current, it is producing magnetic field, and the other sources, of course, the electron itself. So electron itself behaves as tiny magnets. How? Because you have the spin magnetic dipole moment coming in, which is explained very loosely as due to rotation of an electron, and whereas you have another contribution to it, which is orbital magnetic dipole moment, and this is revolution of an electron about the nucleus. Obviously, there is no rotation and revolution as such, but when you imagine this way, it is easier to understand without quantum mechanics. So that's why we generally say like that. So you have magnetic moment arising due to charge motion, and you also have magnetic moment which is arising due to the electron itself. So how do you define the spin and the orbital magnetic dipole moment? This is how it is looking. So when you are having the spin magnetic moment, this is given as mu s. When you have the orbital motion of this particular electron, then you have this mu orbital which is coming in. So this is basically the definition of the spin and the orbital magnetic dipole moments. So now, origin of magnetism, when we talk about the atomic origin of magnetic moments, how it is due to the some is due to the spin of the nucleus and the other is due to the spinning of the electrons. So spin of the nucleus is very small, this contribution is very less, whereas due to the electrons you are having orbital motion of the electrons, you are having spin of the electrons, which I have already explained. So one thing which is important to remember over here is that the magnetic moment due to spin is equal to the magnetic moment due to orbital motion when you are talking about the first Bohr orbit, and this is expressed in the term of a unit which is Bohr magneton. So this Bohr magneton is 9.27 into 10 to the power minus 24 ampere meter square. So I'm sure all of you have heard about the Bohr magneton. So this is just a small revision. So when you are understanding magnetism, you have to understand the different effects which are observed. So what are the different effects? You can have direct coupling. So all these moments, whether it is spin, orbital or nuclear, they are localized to an atom and their direct interaction with moments in the neighboring atoms. This gives rise to something which is the direct coupling. Then you can have something which is known as the mediated interaction. So the moments of the magnetism which is arising from the itinerant electrons in the bands of the metals with the possible of mediation of interaction via free electrons. So this is something which is known as a mediated interaction. And then you have something which is known as super exchange. So here what happens is local magnetic moments, they are interacting with other local moments via the mediation of a non-magnetic element. So what is that? Very easily, if you remember, if you recall, it is the antiferromagnetism in MNO. So basically all the MNs, they are having some kind of magnetic moment associated with it. But in between what you have is the non-magnetic atoms which are present, and but still there is a kind of a super exchange which is happening, and that is why you see this antiferromagnetism in MNO. So from magnetism of the fundamental components to magnetism of devices, this is what the journey is going to be. So what you have is fundamental components of magnetism. As you can see, is this magnetic moment arising due to the orbital motion of the electron. You have the magnetic moment which is arising due to the spinning motion of the electrons. And also you have the spinning of the nucleus, though the contribution of it is very less. So all of this is going to give rise to magnetism, which you see in the atoms. This together is going to give you magnetism of molecules, and together you have the magnetism which is due to the solids. So if you look into the different interactions, the interaction between spin and the lattice is weak. That between spin and the orbital motion is weak, but between the lattice and the orbital motion, this is a very strong kind of an interaction what you see. So now if you look into all the different types of magnetism, all type of matter is going to have inherent diamagnetism associated with it. There is some magnetism which is arising due to the band structure of the metals. These are known as the polyspin paramagnetism, band ferromagnetism, and band antiferromagnetism. We are not going to discuss about this. What we are concerned about in this particular course is which is arising out of the atomic magnetic moments. So you have, these are the permanent magnetic moments which you see, contribution coming from the spin and the orbital motion. So you can have non-interacting atomic moments, and this is going to give rise to Curie paramagnetism, whereas you can have interacting atomic moments, and this is what gives rise to ferromagnetism, ferrimagnetism, as well as antiferromagnetism. So if you talk about diamagnetic materials, how they are, they all have paired electrons. In this case, what is going to happen? The susceptibility is going to be negative. It is temperature independent. And you have, so if you're placing a diamagnetic material within the magnetic lines of force or an external magnetic field, what is going to happen? You will see that these lines of force, they are kind of deflected from this particular material, and this is how it is going to look. So if you are plotting this susceptibility versus temperature, this will look, the susceptibility value comes as negative, and this is, you can see, temperature independent. Whereas if you have a paramagnetic material, they will definitely have unpaired electrons. In this case, the susceptibility value is going to be positive. It will decrease with temperature. Oxygen is one of the prime examples of paramagnetism. And what you see over here is if you're placing a paramagnetic material within this external field, then you will see the lines of force are kind of attracted within the material. So it gets more concentrated inside the material. And this is what gives rise to paramagnetism. And this is how your susceptibility versus temperature plot is going to look like. So you see this particular plot over here. And From this, you get what is known as the Curie law, where chi is equal to C by T. Okay, T is the temperature and C is nothing but the Curie constant. So if you want to understand diamagnetism, one of the most simplified ways of understanding diamagnetism, this is based on Lenz's law. So electrons paired in the same orbital moving with a velocity v, and they are kind of cancelling each other's magnetic moments. And then if you're having a magnetic field which has been applied, increasing magnetic field B on the magnetic moments, then what is happening? You find this M1 is increasing and this M2 is decreasing, so that the net magnetic moment is doing what? It is basically opposing the direction of the applied field. So if you are paramagnetic material, this is how your magnetism versus your field direction is going to look like. So as you increase the field, the paramagnetism, you find the magnetization value is increasing. Whereas in case of a diamagnetic material, you see this decrease. So this is the image plot for a diamagnetic as well as a paramagnetic substance. So what exactly is this paramagnetism? So now there are two distinct types of paramagnetism, one which is arising when the atoms and molecules have a net magnetic moment, and the other which comes from the band structure, which is polyspin or weak spin paramagnetism, which we are not going to discuss in this particular course. So when we will talk mostly about this atoms and molecules, which has a net magnetic moment. So if the net magnetic moment in the atom and molecule, they are not cancelling each other out, then the material is paramagnetic. Oxygen, for example, it is having two unpaired electrons in two different levels, and that is the reason why what you have is a net magnetic moment. The electrons are not paired with each other. So the moment they are paired, then they are kind of diamagnetic. The moment you're getting something unpaired, in that case, it becomes paramagnetic. So please understand that even if there are many electrons in the atom, most of the moments they will cancel out and they will leave a resultant of a few Bohr magnetons. In the absence of any external field, now all these magnetic moments, they point in random direction, and the magnetization of the specimen, the total magnetization is zero. When you're applying a field, the two factors will come into the picture. One is this external field is going to align all these different magnetic moments as per the direction of the magnetic field. And along with it also, there is going to be a disordering tendency of the temperature. So these two opposite forces are going to come into the picture, and ultimately you are going to get some kind of alignment, but there is only going to be a partial alignment. And that is why what you see that the susceptibility of the paramagnetic materials has a very small value. For oxygen, it is almost 1.36 into 10 to the power minus 6 meter cube per kg. So it's a very small susceptibility value. And there are two kinds of paramagnets. So one which are always paramagnetic with no other details to be considered, and others which are like ferromagnetic, ferrimagnetic or antiferromagnetic, and they will turn paramagnetic when you're increasing the temperature. So these ferromagnetic, ferrimagnetic and antiferromagnetic material will have a non-zero theta value, which is basically how Curie-Weiss law was devised. So you had Curie's law, which is giving chi is equal to C by T, whereas Curie-Weiss law is a modification to consider or to factor in all this ferromagnetism, ferrimagnetism, and antiferromagnetism in all these type of materials. And that theta value is nothing but this is known as non-zero theta value all these particular materials are going to have. So now let's see how this is going to look like. If you look into this particular plot where the theta value is kind of positive, you'll find for the paramagnetic materials, if you plot this chi-m versus T, this is how for the Curie law is going to be looking like. Whereas if you have a Curie-Weiss law coming into the picture, in that case, this particular plot is kind of shifted and you have this theta value which is non-zero, and in this particular case, it is positive. This theta value is kind of positive. Whereas in case of the diamagnetic materials, if you look, then this chi-m value is coming somewhere over here. So this dotted line is nothing but giving you the susceptibility values in case of a diamagnetic material. So we have these cooperative magnetic interactions, ferromagnetism, where all the magnetic moments are kind of aligned, and you see this ferromagnetism, so it is kind of reinforcing the magnetic moment. Antiferromagnetism, basically they are also having magnetic moments, but one is opposing the other. So in some case, what is happening, there is going to be one particular direction in which the magnetic moment is going to be more, in the other case it's going to be less. So they are not going to cancel each other out. So you will see a cooperative phenomena, but in this particular case, the magnetic moment value is not going to be as high as that you see in the ferromagnetic materials. And another is ferrimagnetism. This is where basically you will find totally dissimilar magnetic moment values coming in. And the examples of this are in Fe3O4 as well as Y3Fe5O12. So you see all this ferrimagnetism, how it looks like. So all these materials follow the Curie-Weiss law. So chi is equal to C by T plus minus theta. This is how it looks. And this particular plot when you're plotting 1 by chi versus t for the paramagnetic material, you will find that the straight line, it passes through the origin. Whereas when you're plotting it for a ferromagnetic material, this 1 by chi versus t, this straight line is going to pass on the positive direction on the temperature axis. In case of a antiferromagnetic material, what you will find is basically this particular straight line. You have to extend it and it will cross somewhere on the negative temperature axis. And this particular value is known as the Néel temperature wherever it is crossing the temperature axis. In this case, for ferromagnetic materials, your QD temperature is this point where your straight line is crossing your temperature axis. And in case of ferrimagnetic materials, there is going to be a slight bend over here, as you see, and this is how 1 by chi versus t is going to look for a ferrimagnetic material. So now we will talk about the magnetic permeability versus coercive field, how it looks. So if we apply a sufficient magnetic field to produce a complete saturation inside the ferromagnet, then we start reducing the field back to zero. What will you find? Suppose we started from here, we are actually increasing the magnetic field. The magnetization value, it increases, it reaches the saturation point. And from here, if you are applying a reverse field, what you see is that this doesn't come back to zero when you are reducing the field to zero. There's going to be some amount of magnetization which is left, and this is known as the zero. Some residual magnetization is there, which is known as remnant induction, and this is going to remain. And again, you have to apply a little more of this. You have to reduce the field further. And when you're reducing field further, then what is going to happen? This magnetization value is going to come down and it's going to go to zero. And where this point happens, this is known as the coercive field, what you have to apply to completely demagnetize this particular material. So what is this? So this is known as the hysteresis loop. So when we talk about magnetic permeability versus coercive field, this is how this particular plot is going to look like. So you must understand that materials that have a large magnetic permeability, which are these? So we are plotting here coercive field on one side in O state, and we are plotting the relative permeability on the y-axis. You'll find that the materials which have the highest relative permeability, like the med glass or superalloys, they have the lowest coercive field. So basically this entire extended thing, what you see over here, is as narrow as possible whenever you are having a material which is having a very large magnetic permeability. So now we come to the concept of magnetic anisotropy. So what is magnetic anisotropy? It is the dependence of the magnetic properties on the direction of the applied field with respect to the crystal lattice. So it turns out that depending on the orientation of the field with respect to the crystal lattice, one would need a lower or a higher magnetic field to reach the saturation magnetization. So if you remember, we talked about saturation magnetization. It is this particular point. Hysteresis loop, I am sure all of you have seen it, and I'm not going into details of it, but still please remember that that is the saturation value. So when you are orienting the field with respect to a particular crystal axis, you find that the saturation magnetization value is reached either quickly or a little slowly. So we have these different axes, which is known as an easy axis and a hard axis. So easy axis is the direction inside a crystal along which small applied magnetic field is sufficient to reach the saturation magnetization. So you apply a smaller amount of the field strength, and what happens is the material reaches its saturation magnetization value very easily. So that is why the name has been given as easy axis. Whereas hard axis is that direction inside a crystal along which large applied magnetic field is needed to reach the saturation magnetization. So to understand this, please look into this body-centered cubic iron. It has the highest density of atoms in the 111 direction. As you see over here, this is all the atoms are lying in the 111 direction. That is, more number of atoms are lying in the 111 direction. And the atom density is going to be lowest in case of the 100 direction. So what happens is whenever you are having more atoms in that particular axis direction, in that particular that line, what happens is that becomes a very hard axis. So it will take longer time for the material to reach its saturation value, and this is very evident over here. So when you are actually applying this external magnetic field along the 100 line, what you have 100 line, what you see is that the saturation magnetization is reached very quickly. As you can see over here, you are plotting H versus M over here. So this particular H value is much less. Whereas when you are looking into the hard axis, it is reaching the saturation point somewhere over here, and the corresponding H value is much higher. So you have the hard axis where long time is taken to reach the saturation magnetization value, whereas in case of easy axis it is less. So similarly, you can also have it for face centered cubic nickel. In this particular case, when you have an FCC structure, you know that the 111 direction is the lowest pack direction, and so it becomes the easy axis. And in this case, 100 direction is the hard axis. Similarly, you have hexagonal cubic pack structure in cobalt, and in this case, the 0001 is the lowest pack direction, which is perpendicular to the closed pack plane, and it is the easy axis, whereas the 1000 is the closed pack direction, and it corresponds to the hard axis. So similarly, you can see that the moment you are plotting M versus H, this is how basically your plot is going to look. Whenever it is the hard axis, it takes the longest, it takes a large amount of the field, longer time to reach the magnetization value. So please remember, for a material with a single easy axis which is perpendicular to the hard axis, for example, like what you see in case of this cobalt, the energy associated with the magnetic anisotropy is given by this particular formula, where it is EA is basically a summation of K, which is, this is the K is value is the anisotropy constant, and you have sine to the power 2n theta, and this you are summing over all these n values from 1 to infinity. And this is how this is going to look like. So, and theta is the angle between the magnetization, that is your wherever you are applying the magnetization, that direction, and the angle between that and the easy axis. And obviously, as I said, this KUN is nothing but the anisotropy constant. So if you have a cubic material with 3 easy axes, the anisotropy energy is given by this particular equation. And here this alpha values, whatever you see, the alpha I is equal to cos theta I, and theta I is the angle between the magnetization and that between the easy axis. So what is the physical origin of this magnetic anisotropy energy? It is basically the interaction of the mean exchange field and the orbital angular momentum of the atoms in the lattice, and this interaction is referred to as nothing but the spin orbit coupling. So if you have the magnetization angles shown over here and the anisotropy energy, you will see this is how this delta E value is going to change. So this is a very nice pictorial representation of this particular concept, whatever has been discussed over here. So now, how do you derive the hysteresis loop for a single domain ferromagnet? So what is a single domain ferromagnet? So basically you are not having it divided into different domains where you have this different amount. So one domain is where basically you are having all these magnetic moment values, they are aligned in one particular direction. So when we are talking about single domain ferromagnet, what we are talking is inside that all the magnetic moment dipoles, they are all aligned in the same direction. So if we have an anisotropic ferromagnet which is sufficiently small, so it consists of a single magnetic domain. So that is all magnetic dipoles, they are aligned in the same direction, maximizing the total magnetization value M. So you assume that the angle between the magnetization and the easy axis is theta. So in the absence of any external field, the energy of the ferromagnet as a whole is dominated by this anisotropy energy, which we have already discussed, that EA is equal to KU sine square theta. So when the external field is applied to this particular ferromagnet, in addition to the anisotropy energy, you will have something which is known as the magnetostatic or the Zeeman energy. So you now have applied this external field, and originally your M direction was here and this was the easy axis. So this theta value is basically the angle between the total magnetization value and the easy axis. Whereas when you're applying this H particular, this external field, this total angle with the easy axis is phi. So the angle between these two is phi minus theta, and this is what is given over here. This magnetostatic energy is given as H ms cos phi minus theta. So H is the applied magnetic field, ms is the saturation magnetization, which you see over here, and phi is the angle between the applied field and the easy axis. So this is the thing. So now what is the total energy when you have this external field which is applied? So this is actually the anisotropy energy plus this magnetostatic energy, whatever you see. So now there are two important special cases for the direction of the magnetic field. It can be either along the easy axis or along the hard axis. So if it is around the hard axis, then this phi value is pi by 2 or 90 degrees. So now if you put it in this particular equation, this phi value as pi by 2, then this particular equation changes to this E value is nothing but Ku sine square theta plus HMS sine theta. Simple maths. So now if you derive, the hysteresis loop for a single domain ferromagnet, by finding the angle that minimizes the energy in this particular case, if you solve this entire thing, if you look into it later on, this is not something which I will be explaining in the class, but when you have some time, you can go through it. This is just for your own understanding. It's very difficult to go through the derivation, in this kind of online class. But you can find that for the hard axis magnetization, for any hard axis, the magnetization changes linearly with the applied field until it reaches the saturation. So it will change linearly. So along the hard axis, magnetization is going to change linearly with the applied field until and unless it reaches the saturation point. Okay. But when you look into the easy axis magnetization, please remember this was derived for the hard axis where phi was equal to pi by 2. But when you have the easy axis, then this phi value is 0. If the phi value is 0, then for this particular equation, this E value is becoming Ku sine square theta plus HMS cos theta. So now again you have to find out the minimum and the maximum values for all the magnetic field values, whatever is given. And in this case, you'll find there is a coercive field value which is coming as 2 Ku by ms. And all of these fields are going to yield, saturation magnetization. And the result is an ideal rectangular shape of the hysteresis loop. So if you look into the hysteresis loop now, whatever I tried telling over, in the last 2-3 slides, the main result is this. So if you have your magnetization, this value along the easy axis, in that case you should get this rectangle, and if you have it along the hard axis, then this is how this is going to change. Okay, so for the easy axis you will get this box kind of structure with the coercivity value, whereas if it is for the hard axis, there is no coercivity, or m value it increases as you are increasing the external magnetic field. So this is basically the idea. So an ideal hysteresis loop should somewhat look like this, but it doesn't look like that because you have some losses which are there. So now what is a permanent magnet? So if you're having a permanent magnet, you will have a very high coercivity value. There's going to be a lot of mr, which is the remanence value or the remanent magnetization which is there, and it is going to have a very high tc, which is the Curie temperature. So these are so when you are having a permanent magnet, this is the quality which you are looking for. When you look into the hysteresis loop, you should see that if the material is having a high coercivity, high remanent value, and it has a high TC, then it is going to be a material which is used for permanent magnets. Whereas when you are looking for something which should be applicable in transformers, you are using something which is having a very low coercivity and you are having a very low remanent magnetization value. For information storage also, you are looking at soft magnets with unique hysteresis loops. So this is the kind of, for information storage, these are the kind of loops you are looking into. So now we'll talk about the alignment of domains which leads to magnetization of the sample. So whenever we are doing this, when we are increasing the external magnetic field, you find that the magnetization increases in this particular way, right? You have this kind of S-shaped curve. So there is a steep increase and then followed by a kind of a slow increase of the magnetization value until and unless it reaches the saturation point. So why this is happening? So you have to understand, whenever you have a particular magnetic material, so you are having many domains present in it. As I said, in one particular domain, all the magnetic dipoles are aligned. But when you have multiple domains, in all these different domains, all these magnetic moments are aligned in one direction, but domain to domain, the alignment differs. So what happens is, now when you are kind of applying this magnetic field, so all these magnetic moments in the different domains, they are aligning as per the external magnetic field direction. So this can occur by either a domain wall motion, which can be smooth or jerky, and it can also happen by rotation of the magnetization of the domains. The external magnetic field will tend to align the misoriented spins in the domain wall, leading to its displacement. And these processes can occur simultaneously as the field increases. So you must understand this. So what is happening? So this great increase in the magnetization value is first due to the domain wall motion. So what happens is, you are pushing the domain wall and you are increasing the magnetic dipole alignment in one particular domain, and you are pushing all the other domains, you are reducing the size of the other domains. And then what happens is, the entire wall rotation also happens, and in that particular case you find the increase in the magnetization value is much less. As you can see over here, it grows slowly, and ultimately when all of these are aligned as per the external magnetic field, you reach this saturation value. You must understand, the rotation of the spin is opposed by an increase in the anisotropy energy. Okay, magnetocrystalline shape stress. So when you are rotating the spin, then you are it doesn't like the rotation of the spin because it is increasing the anisotropy energy in the material. So during rotations, all spins need not be parallel to one another, and the actual picture, of course, it can be a little more complicated than the way we are explaining. But the idea is this, that you have a domain wall motion, and this is followed by a domain wall rotation. So what is going to be the effect of temperature? So spatially correlated collective quantized modes leads to the demagnetization, or called spin waves or magnons. So ferromagnet becomes paramagnet above Curie temperature. So at Tc, what is happening? Your susceptibility is becoming infinite. Even beyond Tc, sometimes you will find local clusters are present, which are known as spin clusters of allied magnetic moments. And maximum magnetization is obtained when all the moments are having parallel orientation. And this state corresponds to a magnetization M0 or sigma 0. So when you are plotting basically the saturation magnetization by M0 and against the temperature versus the Curie temperature, you will find that for all ferromagnet, this is going to be the particular curve. This is known as the demagnetization curve for a ferromagnet. So this Ms by M0 at T by Tc, if you are plotting for any kind of ferromagnetic material, it is this particular point where this entire thing gets demagnetized. So the ferromagnet gets demagnetized. So what is the domain structure and the magnetization process? The magnetic structure of a ferromagnetic material, as I said, consists of domains. Why? Because it will reduce the magnetostatic energy. So domains, these are separated by domain walls. So there are two types of domain walls. One is known as the block wall and the other is known as the nail wall. So what happens in case of the block walls? The spin vectors rotate out of plane in the domain wall. So you see over here you have this domain 1 and domain 2, and you look into the alignment over here. So one is moving from left to right as shown in this particular slide, and in the other case domain 2, it is moving, the direction of the magnetic dipole is from right to the left. So now in between the domain wall, what is happening from one domain to the other to reduce the energy? Inside the domain wall, you will have the spins which are aligned in this particular way, and they are kind of all the spin vectors, they are rotating out of plane in the domain wall. So usually the domain wall thickness is a few hundred atomic diameters, that is, it is rather diffuse. Hence the domain wall by itself, if you say, this is a nanostructure. So this is a block wall, and this you see when there is a thick domain wall. When if it is a very thin domain wall, then it is generally known as a Neal wall. And these are generally observed, Neal walls are generally observed in very thin films which are less than 40 nanometer thick. So this domain wall, they represent a region of very high energy, as the spin vectors, they are not in the direction of the easy magnetization. Hence, thicker walls will represent higher energy, and in materials with higher magnetocrystalline anisotropy energy, the domain walls are going to be very thin. Other sources of anisotropy are due to the shape of the particle and due to the residual or applied stresses. So there is a competition between the magnetostatic energy and the magnetocrystalline anisotropy energy, and this essentially will decide the domain size as well as the shape. So you have other factors also included in this entire energy thing. One is the magnetoelastic energy, which is due to the magnetostriction or change in dimension due to a magnetic field, and this will also contribute to the overall energy. So the total energy, what you see, can be written as a sum of four terms. You have exchange energy, you have anisotropy energy, you have magnetoelastic energy, and you have external energy. And this external energy, it corresponds to the energy of the total magnetic moment in the external magnetic field. So if you see, this is the total contribution to all these different energy values, what you see over here. So now coming to magnetostriction. What is magnetostriction? So as the name suggests, a magnetostrictive material which change shape when you are placing it in a magnetic field. So now most ferromagnetic materials, they exhibit some measurable magnetostriction. This phenomena, it involves a bidirectional energy exchange between the magnetic and elastic states, and these materials provide a mechanism for actuation and sensing applications. So these kind of magnetostrictive materials, they are used for in actuators and in sensors. And they are also used in a wide variety of devices for vibration control of mechanical equipment. So what is the idea? So when a current, suppose, is flowing through the length of, when the current is flowing, what happens? This length of the rod, whatever is there, this kind of increases by a small amount, like delta L. So if it was L, once the current is applied, you see the length of this rod increases. It's a very minuscule amount. And this strain, this delta L by L, is called the magnetostriction, and for which the symbol lambda is used. And please remember, this magnetostriction is a second order effect. So the principal magnetostrictic effects which are observed experimental are, one is the Joule effect. So this can be an extraction or a contraction in the same direction as in the magnetic field or in some other direction. You can have a volume effect, volumetric expansion, which is a very weak effect again. Then you have the Weidmann effect, which is a shear strain response to the magnetic field, which is analogous to the tensile or compressive strain which is produced in the Joule effect. And the fourth point is the Villari effect. This is a change in the magnetic permeability in response to the applied stress. So this is also referred to as a magnetostrictic effect or a magnetomechanical effect. So please understand, you can also observe a change in the magnetic permeability in all these materials, which shows this magnetostrictive value. So now obviously why it occurs. So when an external magnetic field is created, the domains which are aligned most closely to the external field will grow, while all the other domains will be reduced in size. As I said, because you are having the domain wall motion, if you remember that M versus H curve which we discussed extensively. So depending on the orientation of the crystal, there will be some cases where electron orbitals cannot become aligned to the direction of the external magnetic field without a change taking place in the distances between the atoms or ions. So now these distances must increase to allow these orbitals to become aligned. And then what is happening once this distance between these atoms or ions are increasing, then there's a change in the length, and this causes the crystal structure to become elongated in the same direction as the magnetic field, or they may become elongated in one or more directions at right angles to this particular direction where the magnetic field is applied. So in this last case, there may also be a contraction of the crystal in the same direction as the magnetic field. So if it is elongating in one side, then it is kind of getting constricted in the other side. So it depends, like it can be either there can be an elongation, or sometimes there can be also a kind of a compression or a contraction. So now that was magnetostriction. Now you have something which is known as magnetoresistance. So what is this? As the name suggests, the resistance of a conductor will change when it is placed in an external magnetic field. So obviously this is known as magnetoresistance. The resistance is going to be higher if the field is parallel to the current and lower if the field is perpendicular to the current. In general, the resistance depends on the angle between the current and the magnetic field, and this is called as anisotropic magnetoresistance, or AMR. And this change is usually small, 5%. And normally for most of the materials it's around 5%. In some materials like ferromagnetic uranium compounds, you will find it to be as large as 50%. And magnetoresistance is arise from a larger probability of SD scattering of the electrons in a direction which is parallel to the magnetic field. And this AMR effect is mostly used in magnetic field sensing devices. Okay. Now we have something which we need to discuss again, is magnetism in nanomaterials. So you have to understand that magnetic nanostructures are even present in bulk materials, where like in the domain walls in a ferromagnet, as I explained in the block wall, some domains, especially those which are in the vicinity of the surface or grain boundaries, they could themselves be nano-sized. Then you can have spin clusters which are above the paramagnetic Curie temperature. This could be nano-sized. So when we are going from bulk to nano, only the structure sensitive magnetic properties like coercivity is expected to change significantly. The other properties are not going to change, but coercivity is a property which is structure sensitive, and this is going to change when you're moving from the bulk to the nano. And some of the possibilities which can be there when we are moving from a bulk material to a nano material, when the material is the same, then the ferromagnetic particles can become single domain. Then you will see super paramagnetism, very small ferromagnetic particles. They will show something, a property which is known as super paramagnetism. You can have giant magnetoresistance effect in hybrids, which is in layered structures. And then you can have antiferromagnetic particles in bulk, which will behave like ferromagnets. So all these different things are possible when you are moving from a bulk material to a nanomaterial. So there is an increase in the magnetic moment per atom as we decrease the dimensionality of the system. And why this happens is because on the surface now you have many spins. So when you're bringing down the size, then what happens? The surface spins they are not ordered along the same direction as the spins in the interior of the material. They are kind of balanced by the spins in all the other areas of the material. So in the interior of the material, when the spins are in different direction, you will have, because there is more material, there will be other spins which will be exactly the opposite of that, and so they ultimately cancel each other. But on the surface, what is happening? These spins, they are kind of staying not ordered along the same direction. So what is happening? These unpaired spins, they will give rise to some kind of magnetic moment. So this is what you see in the bulk material for iron. If you see the magnetic moment, which is Bohr magnetons and given in Bohr magnetons, if it is 2.27 in the bulk material, by the time you move to a 0D iron, in that case, this magnetic moment has increased to almost 4 Bohr magnetons. So this is a very important concept. Then there is another concept which is superparamagnetism. As I said, as the size of the particle reduces, the whole particle becomes a single domain below a critical size. So what happens? A particle which is smaller than the domain wall thickness cannot sustain a domain wall, obviously, because the domain wall thickness may not be constant with size. And so what happens? The magnetostatic energy, it is increasing as a factor of r cube. R is the radius of the particle, and the domain wall energy is a function of r square. So obviously there is going to be a critical radius below which the domain walls are not stable, and that is the reason why you cannot have multiple domains once the size is kind of decreasing. So the general trend is this RC value is a function of sigma by this ms square. Ms is the saturation magnetization. So what you see is as this radius of the particle, it decreases, the critical radius, as small it is, this ms value, saturation value, is kind of inversely proportional. So you have a larger magnetic saturation magnetization when the size of the particle is small. And this is which is giving rise to this superparamagnetism. Then you have how basically when you are changing the size, when you're moving from a larger size to a very smaller size, how this happens. So you have this multi-domain area when you're moving from the micrometer size, you're bringing down the size. So you have domain wall motion where ultimately your magnetization value is increasing because it is getting aligned. All these magnetic dipoles are getting aligned. And then what happens, you have a particular place when you're just reaching the peak coercivity is happening at this particular diameter. When it is reached a kind of critical diameter, what is happening? You are having the highest amount of coercivity in this particular case. And then if you're bringing down the radius of the particle even lower, so then what happens? You're having a single domain, and now the domain wall rotation is happening over here. You can see this domain wall rotation happening. And then if you bring it down even below this particular diameter, then the thermal disordering effects is coming into the picture. So again, your materials are going to get disordered, and so thermal disordering effect will dominate over tendency for spin alignment, and ultimately you will see that this coercivity value is going to decrease. So what you have, multi-domain, that is increasing coercivity with decreasing size. For single domain, you have a peak coercivity. Then single domain, there is going to be a decreasing coercivity with decreasing signs. And ultimately in the single domain itself, there is going to be a point when this thermal disordering effect is going to completely take over, and what you will see is a zero coercivity. So this is what is expressed over here. For a superparamagnetic material, this is how your M versus H by T curve is going to look like. So this is known as a superparamagnetic nanomaterial. Now you have something which is known as exchange anisotropy, and this you see in magnetism of hybrids. So there is going to be an exchange coupling of spins across an interface. If you have a ferromagnetic phase and an antiferromagnetic phase which are adjacent to each other, so what is going to happen? There is going to be an exchange coupling of spins across an interface, and there is going to be a preferred direction or anisotropy for the field, and this is going to lead to a shift in the hysteresis loop. So whenever you see exchange coupling, so when you remember this hysteresis loop, whatever we had seen M versus H, you will find that instead of the coercivity value becoming equal on both sides of that H value, there's plus H and minus H is equal, it is equal. Instead of that, you will see a shift in one particular direction. And the moment you see that kind of shift in experimental results, you know that this particular material is having exchange coupling. So what are the steps which are involved in creating exchange anisotropy? You have a single domain ferromagnetic particle, suppose cobalt, in contact with an antiferromagnetic layer like cobalt oxide. You're applying a field above the Néel temperature of the antiferromagnetic phase to saturate this ferromagnetic phase. And you cool the system below this Néel temperature of the antiferromagnetic phase to introduce a preferential alignment of the spins across the interface, that is in the antiferromagnetic phase. And the spins in this ferromagnetic phase will now maintain their orientation even after you remove the field. So then you construct the usual M versus H loop. So if the field is removed, the spins in the ferromagnetic phase, what it will do, it will flip to the field orientation due to the influence of the antiferromagnetic phase. So as the field direction gets reversed, the spins across the interface in the antiferromagnetic phase, antiferromagnetic material, this will oppose the reversal of the spin in the ferromagnetic phase. So hence this exchange coupling is going to lead to a very large coercivity value. So all what I said over there is explained over here. So the usual position of your MH curve is like this. So whenever there is going to be an exchange anisotropy, which you will definitely find in hybrid materials where one layer is ferromagnetic and the adjacent rail is antiferromagnetic, you will find that the MH loop is going to shift and you will have a much higher coercivity. So this is known as exchange coupling. There are some very important properties when you talk about magnetic materials. This is one is known as the zero field cooled and the field cooled curves. So what you do is you take a sample and you cool it in the zero field from T1 where all the particles are super paramagnetic to a T minimum, and this is done at a constant rate. Then you apply a very small measuring field which is applied at this minimum temperature, and then you're heating the sample from this minimum temperature up to a high temperature and you're measuring the magnetization value. So this is known as a zero field cool measurement being done. Then followed by that, what you have is a field cool. In this case, what you do, you are cooling the sample under an external magnetic field from T1 to T minimum at a constant rate. And then you're heating the sample from this T minimum to a high temperature and you measure the magnetization. So this is the field cooled magnetization. So what you will see. So in this case, what you will see is when it is field cooled. So this is the ZFC and the FC curves. So what you have is above. So in one case, when it is field cooled, it is going to look like this. You can see this flattening, and when it is zero field cooled, it is going to look like this. So what you have is at this point, there is going to be a T irreducible temperature over here. And this T irreducible temperature is the T max, or this is known as the blocking temperature. So please remember, just above this blocking temperature or this irreducible temperature, this lifetime value is so short that the thermal equilibrium is always attained before completing a single measurement. So it becomes a super paramagnetic state. So please understand that above this particular blocking temperature, this is how your plot is going to look. The chi value is going to look like this. Chi versus T value is going to look like a super paramagnetic state. Okay. Look at this particular plot. This is how the chi versus T is looking for in case of a paramagnet. So this is how this is going to change. So this is the ZFC and the FC measurements. So what are the application of magnetic materials? You can have hard magnetic materials. So look into this particular plot. Over here, I've given a few materials like steel, ferrite, alnico, SMCO or NDFEB. So these are different kinds of materials which are hard magnetic materials. And you look into these different sizes. Why? Because this is the relative magnetic volume for the same magnet energy. So maximum energy which is produced by steel as a magnet, if you need this much amount, then if you are using NDFEB, with this much amount of volume, you are able to generate the same amount of magnetic energy. So obviously, you have to understand that these particular hard magnetic materials, they find a lot of application in various things like in automotive industry, where you're using it for motor drives for fans and wipers and injection pumps, control for your seat, windows, etc. So these hard magnetic materials are used. Then in telecommunication, you're using it in microphones and loudspeakers, in telephone ringers. In data processing, you're using it in printers, in stepping motors, and disk drives. Consumer electronics and the computers, clocks, DC motors. Then in electronics and instrumentation, energy meter discs, sensors, dampers, etc. In industrial applications for lifting various apparatus, in robotics, meters. In aerospace industry, you're using it for auto compass, for couplings, instrumentation, and in biosurgical for NMR and MRI body scanner. All these hard magnetic materials find a lot of applications. So not only the hard magnetic materials, the soft magnetic materials have also tremendous applications. So what are these soft magnetic materials you can think about? There can be cobalt-based amorphous alloys, and of course there is iron. So you can see how it is. They are having a lot of application in power electronics, like in generators, in distribution transformers, and a broad assortment of motors, as well as in electronics, where a mass of inductive components are required. So soft magnetic materials, when you're looking into direct current applications, the material is magnetized to carry out an operation, and then it gets demagnetized at the last part of the operation. And when you are selecting materials for DC application, you have to consider the permeability. High permeability is required for good material, and this is used in the field of magnetic shielding, electromagnetic pole pieces to activate the solenoid switch. Permanent magnet uses this material to make a path for the flux lines. Whereas when you are using it in alternating current applications like AC applications, The material has to be always in the magnetized state throughout the time of operation, and it is done by being magnetized in one direction to other as a continuous cycle. And for material selection, now this case, the main consideration is the energy loss in the system. So the energy loss occurs because the material is cycled around the hysteresis loop. A good material should have small energy loss, and this is generally used in power supply transformer, DC-DC converter, electric motors for making a path of flux in permanent magnetic motors, etc. So this is how there is going to be a lot of application. There are some futuristic application, a lot of application of magnetic nanoparticles. You can use it in conjunction with dyes, and you can use it for multimodal imaging. You can have a lot of ligands or receptors on these magnetic nanoparticles, and you can use it for bacteria detection, for protein separation. You can have antibodies or DNAs kind of, arranged over these magnetic nanoparticles, and then you can use it for specific binding drug delivery kind of applications. You can have quantum dots, and that can be used as multimodal imaging, nano drugs for drug delivery or MRI. And you can have these different metal magnetic nanoparticles, which can again be used for multimodal imaging using the SERS application and stuff. So coming to magnetoresistance, as I said, magnetoresistance is the dependence of the electrical resistance of a sample on the strength of an external magnetic field. So what you have, RH is the resistance of a sample in the presence of magnetic field, this when there is no magnetic field, and this when you are the difference of this when you are actually making a ratio with the resistance when there is no magnetic field. This value is known as the change in the resistance, and this indicates that there is a change in the resistance when you are putting the material in a magnetic field. Now that is simple magnetoresistance, but some materials show extreme amount of this magnetoresistance, and this is termed as giant magnetoresistance. And this value, this delta H value for multilayer structures significantly exceeds the anisotropic magnetoresistance, because as you remember, I told you this typical value is between a few percent, whereas when you talk about giant magnetoresistance, it can be like 40-80%. Like you can have this kind of delta H values for this. So this was discovered by Grunberg and Furt in 1988. And this is a large change in the electrical resistance, which is induced by the application of a magnetic field to thin films composed of alternating ferromagnetic and non-magnetic layers. So what happens is basically this entire thing you can read later, but you must understand what is happening. The origin of this giant magnetoresistance is the dependence of the electrical conduction in ferromagnetic materials on the spin state of the carriers, which is the electrons. So what exactly is this? So you are having two layers of this very thin layers of this ferromagnetic material, one with M1, one magnetization value M1, the other with M2. And then what you have is a non-magnetic layered material in between. So now what is happening, these materials is going to have some resistivity, and this resistivity value is going to change the moment you are passing an external magnetic field to it. And this resistance value, what is changing, this is being defined as the GMR effect in magnetic multi-layer systems. So there's a change in the electrical conductivity in a system of metallic layers when an external magnetic field changes the magnetization of the ferromagnetic layers relative to each other. So when you apply the field, what happens is this particular direction is changing, and this external change, this gives rise to this magnetoresistance. So you must understand that the spectrum of successful applications of GMR technology is impressively broad. It ranges from application in the air and space or automotive industry. It is used in non-destructive material testing or the compass functionality in mobile phones, and also it is used in biomedical techniques like biometric measurements of the eyes, biosensors, for example, in the detection of viruses. So there's a lot of application of giant magnetoresistance effect. So if you look into it, so this is how your material is looking like. So the resistance, if you look for this particular stage, it is going to be somewhat like this. You are plotting the resistance versus the applied magnetic field. So the resistance is somewhere here. And then when there is a flip with the application of the magnetic field, what you are having over here is a very giant, there's a leap in the resistance value. And then again, when it is flipping onto the other side, again you see the resistance value is changing. So ultimately, what is this? What you are having? The magnetizations are aligned anti-parallel at the zero field, and the magnetizations are aligned parallel when the external magnetic field is larger than the saturation field, which is the HS. So the magnetization curve for the multilayer is going to look somewhat like this. So your material was here, and then you have applied the magnetic field. When the coercivity or magnetic field is higher than that of the saturation field, in that case you will find that this entire the way it was aligned, it just changes. Similarly, it happens on the other side also, and this is how the magnetization versus your the magnet external magnetization saturation magnetization value is going to change with the applied magnetic field. So what is the origin of the GMR? So this is basically the electrical conductivity in metals. This is described in terms of two largely independent conducting channels, and this corresponds to the upspin and the downspin electrons, and these are distinguished according to the projection of their spins along the quantization axis. So the upspin and the downspin electrons, they do not mix over long distances, and therefore the electrical conduction occurs in parallel for two spin channels. So you have something which is known as upspin electron, and you have something which is known as a downspin electron. And the band structure in a ferromagnet is exchange split, so that the density of states is not the same for the upspin and downspin electrons at the Fermi energy. So scattering rate is proportional to the density of state. So the scattering rates and therefore resistivities, they are different for electrons of different spin. So this is the main idea. So you have to understand the resistivities are different for electrons of different spin. So when the scattering is strong, so there is one thing. It is assumed that the scattering is strong for electrons with spin anti-parallel to the magnetization direction and is weak for electrons with the spin which is parallel to the magnetization direction. So this is supposed to reflect the asymmetry in the density of states at the Fermi level in accordance to the Mott's second argument. So for the parallel aligned magnetic layers, the upspin electrons will pass through the structure almost, without any scattering, because their spin is parallel to the magnetization of the layers. On the contrary, when you are having these downspin electrons, they are scattered strongly within both paramagnetic layers because their spin is anti-parallel to the magnetization of the layers. So now you see over here, this is upspin and this is downspin. So this is how it is going to look. And when it is upspin and downspin in both directions, so you will find the scattering is very strong when you are having the downspin electrons in both the layers. So now since conduction occurs in parallel for the two spin channels, the total resistivity of the multilayer is determined by the highly conductive upspin electrons and appears to be low. And when you have the anti-parallel aligned multilayer, both the upspin and downspin electrons are scattered strongly within one of the ferromagnetic layers, because within one of the layers the spin is anti-parallel to the magnetization direction. Therefore, in this case, the total resistivity of the multilayer is also going to be very high. So this is the origin of this magnetoresistance effect. Please understand it is due to the conductivity of the electrons which are there, and for the upspin and the downspin you have different conductivity. And for one case, the scattering is going to be more with the external magnetic field. In the other case, it is going to be low. And that is why you see this kind of a giant magnetoresistance effect. So there can be different types. So in this particular case, you see how it is. It is in the magnetic layer A, the ferromagnetic layers are separated by non-ferromagnetic spacer layers. So due to the antiferromagnetic interlayer exchange coupling, they are aligned antiparallel at zero magnetic field. And this is indicated by this dashed and the solid arrows. At the saturation field, the magnetic moments are aligned parallel, and so you find all these solid arrows, whatever you see. So this is for a magnetic multilayer. B in this case is for a pseudo spin bulb. C is for a normal spin bulb, and G is for a granular thin film. So these are all these different types of GMR materials. When you're having this pseudo spin bulb, the GMR structure combines both hard as well as soft magnetic layers, and they have different coercivities. So the switching of the ferromagnetic layers occur at different magnetic fields, providing a change in the relative orientation of the magnetization. In case of the spin bulb, what is happening? The top of the ferromagnetic layer is pinned by the attached antiferromagnetic layer. As you can see, this top of this ferromagnetic layer is pinned because you have this attached antiferromagnetic layer. And the bottom ferromagnetic layer is free to rotate by the applied magnetic field. And in case of the granular material, magnetic precipitates are embedded in the non-magnetic metallic material. In the absence of the field, the magnetic moments of the granules are randomly oriented, and the magnetic field aligns the moments in a particular direction. So what are the applications of this giant magnetoresistance effect? It is definitely in the data storage industry. The GMR read head sensor in a hard disk is built using this kind of spin bulb, and the spin bulb resistance demonstrates a steep change in the small field range, which is close to zero. As the magnetic beats on this hard drive, they pass under the read head. The magnetic alignment of the sensing layer in the spin bulb changes, and this results in basically resistance change. So this is basically the application of GMR. So as the reader is passing over the disk, the free layer shifts its magnetic orientation. It will to match that of the bit. So sometimes the direction of the free layer's magnetic field is aligned along with the field of the pinned layer, which never changes, and sometimes it is opposite. So when they are aligned, most of their electrons will share the same up or down spin. As some of these electrons will pass through the layers in the form of current, there is going to be minimal scattering. And the low resistance means the current will be detected and the computer computes a one-bit thing. So when the free layer's magnetic orientation switches to the opposite that of the pin layer, then there is going to be a much different result. So the electrons in the two layers have opposite spins. So as the current passes through the magnetized layers, those electrons will scatter in one or the other of them, resulting in a much weaker current. And so now you will see a zero bit. So this is how this sensing is happening. So that is basically the application of GMR. Now coming to ferroelectric. So that was, we covered magnetostriction, we covered magnetoresistance, we covered giant magnetoresistance, how these concepts are and how basically you are using GMR to have a read head using these kind of GMR materials. Now we'll talk about another interesting concept, which is ferroelectrics. So ferroelectricity, you should understand, is a characteristic of certain materials that have spontaneous electric polarization. So for magnetic materials, you found magnetic polarization. In this case, you'll find electric polarization, which can be reversed by the application of an external electric field. So if you apply a small electric field such that it is not able to switch domain alignments, then the magnet material is behaving as a normal dielectric. So this polarization is directly proportional to the electric field. Now as the E's increase, we start to flip the domains and we rapidly start increasing this polarization. So when all the domains are switched, we are reaching saturation. So now what will happen if this particular field is removed? Again, you will see the same thing, that when this field is removed, you will see some amount of remnant polarization, and this is known as the electric polarization hysteresis, or this type of material is known as a ferroelectric material. Okay, the essential feature of a ferroelectric is not that it is spontaneous polarization, but that the spontaneous polarization can be reversed by the application of an electric field, and you will find this kind of coercivity also present in case of a polarization hysteresis. So the crystal classification of a material, this has immediate implications for ferroelectric effects. So please understand there are 32 crystal classes as shown over here. So out of them, 11 have a center of symmetry. So they are centrosymmetric and they will not support ferroelectricity. So those 11 are given in black over here, as you can see. So now of the remaining 21, the O point group, that is this O point, whatever you have, this also excludes ferroelectricity. So you don't see ferroelectricity for that group also. The remaining 20 classes, they all exhibit what is known as the piezoelectric effect. So you can understand, so this is this entire piezoelectric material, and among which you have something which is known as a pyroelectric material, and in between this you have something sitting which is known as the ferroelectric. So 32 point groups, you have 11 which are centrosymmetric. So obviously they are not coming in this polarization hysteresis, you will not see. 21 are non-centrosymmetric. One is an exception, so that is there. Out of this 20 which are piezoelectric, you will have 10 polar groups and 10 non-polar. Out of this 10 polar or pyroelectric materials, for some you will see this reversible polarization, which is ferroelectric, and the others are non-reversible polarization, which doesn't show as ferroelectric material. So the idea is, out of these 32 point groups, you have 21 non-centrosymmetric, 20 of them are piezoelectric, 10 are polar, and out of this, whichever is showing reversible polarization, they are ferroelectric materials, and this is the idea between crystal symmetry and ferroelectric materials. So perovskite is one of the prime examples of ferroelectric material. So perovskite is a naturally occurring mineral, and it has the formula of CaTiO3, which is calcium titanate. And this is a prototype for many AbO3 materials, and these are very important in ferroelectrics. These materials may be envisaged by considering a non-polar cubic based building block. So you can see over here, the B material is sitting over here. All of this is your A, these blue ones, and your oxygen is sitting in all the 6 faces, center of the face. The perovskite structure. So below the Curie temperature, these metal crystals will undergo symmetry lowering distortions. So there are 3 phase transitions in these barium titanate in order of decreasing temperature. So you will have at 120 degrees centigrade, 5 degrees centigrade, and minus 90 degrees centigrade. So you will see all these different kinds of elongation and contraction which is happening. Finally, the lowest temperatures yield rhombohedra, which is the rhombohedra, which is distortion along the body diagonal. So you see along the body diagonal, you're kind of pulling it. And there are therefore 8 equivalent distortion directions. The solid exists in one of the 4 polymorphs depending on the temperature. From high to low temperature, these crystal symmetries of the 4 polymorphs are cubic, tetragonal, orthorhombic, and rhombohedral crystal structure. All of these phases exhibit the ferroelectric effect apart from the cubic phase. Of course, you understand why, because that is symmetry. So you have the tetragonal, orthorhombic, and rhombohedral crystal structure, and all these phases will exhibit ferroelectricity. So now we come to something semiconductor memory technologies. Why? Because ferroelectrics are used in that. So RAMs are basically random access memories. You have heard so much about RAMs, and these have a symmetric read and write access time. So non-volatile memories that have traditionally read-only memory, that was until the advent of the floating gate technology. So floating gate technology produced electrically erasable memories such as the flash and the EEPROM. So these products allow for in-system programming, but read and write access times are dissimilar. In fact, the write access times, it can be several orders of magnitude, which is greater than the read access time. So ferroelectric random access memory, or FRAM, is a true non-volatile RAM because it combines the advantages of both this random access memory and the non-volatile memory. So the write advantages over this flash or EEPROM and non-volatility makes it quite suitable for storing data in the absence of power. So these ferroelectric materials are used for this FRAM technology. So this floating gate basics I will not cover, but I'll just talk to you about what is a ferroelectric RAM. So this FRAM memories, they are built on this ferroelectric technology. So FRAM chip contains a thin ferroelectric film of lead zirconate titanate, commonly which is known as PZT. So the atoms in the PZT, they will change polarity in an electric field. So it will produce a power efficient binary switch. However, the most important aspect of this PZT is that it is not affected by power disruption, and that is why it makes this FRAM a very reliable non-volatile memory. So please understand the cation in the center, that is this B cation, what is happening, it has 2 equal stable and low energy states, and these states will determine the position of the cation. So applying an electric field across the crystal causes the low energy state or position to be aligned in the direction of the field, and conversely, the higher energy state will be in the opposite position. The applied field will therefore cause the cation to move from the high energy state to the low energy state, and this transition produces energy in the form of a charge, and generally which is referred to as the switch charge. This is QS. Therefore, applying an alternating electric field across the crystal will cause the cation to move from the top of the crystal to the bottom and back again. So how this operation takes place for this FRAM. So the basic storage element is the ferroelectric capacitor. The capacitor can be polarized up or down by applying this electric field. Why? As I explained before. So if a ferroelectric capacitor is not switched when an electric field is applied, so there is no change in polarization state, so it will behave like a linear capacitor. Now if it is switched, there is an additional charge induced, therefore the capacitance must increase. The ferroelectric capacitor is combined with an access transistor, a bit line, and a plate line, and this forms a particular which is known as a memory cell. So a write operation, it becomes very similar to a read operation. The circuit applies an electric field in the desired direction across the ferroelectric capacitor. So this is how the FRAM operation takes place. Now we come to something which is known as the magnetoelectric effect. So we have understood now what is that entire, ferromagnetic materials, and now we also talked about ferroelectric materials. Now there is going to be a coupling between the two. So this is known as a magnetoelectric effect. This is characterized how by a variation of the electric polarization. You will see, there is going to be a change in electric polarization in response to an external magnetic field, or there is going to be an induced magnetization by an external electric field. So now what is happening in previous cases, what we saw that we are seeing a polarization because you're changing the magnetic field. You're seeing a change in magnetization because of an external magnetic field. You're seeing a change in the electric polarization because of an electric field which is applied. But magnetoelectric effect is different. What is happening? You are applying a magnetic field and you're seeing a change in the electric polarization. Or whatever you're doing is that you're applying an electric field and you are having an induced magnetization effect coming in. So this is how this is kind of expressed. So this P value is going to give you as chi E plus chi EMH, and M is chi MH and chi MEE. This chi E is electric susceptibility tensor, and this chi M is the magnetic susceptibility tensor. And this chi IJEM and ME, this is the mixed magnetoelectric susceptibility tensor. So ultimately, what you have over here is nothing which is known as the magnetoelectric effect. So what is this magnetoelectric effect? Is the phenomena of inducing magnetic or electric polarization by applying an external electric magnetic field, depending on the case. So when you are inducing magnetic field by an external electric field, that is also magnetoelectric effect. And if you are inducing an electric field by applying an external magnetic field, that is also a magnetoelectric effect. The effects, it can be linear or non-linear with respect to the external fields. In general, this effect depends on temperature, and this effect is expressed in the following form. So this is how you will see how this particular, all these things are kind of interrelated to each other. So you have all these different. So when you are having magnetoelectric effect, it is the coupling between the electric field and the magnetization value. And you can have a direct magnetoelectric effect, or you can have a converse magnetoelectric effect. So what are multiferroics? Multiferroics are defined as materials that exhibit more than one primary ferroic order parameters in the same phase. So this leads to the formation of switchable domains. So ferromagnetism is spontaneous magnetization, ferroelectricity is spontaneous polarization of the electric field, and ferroelasticity is spontaneous strain. So if you have ferroelectric and ferroelastic material coupling with each other, what you have is piezoelectric and electrostrictive coupling. If you have ferromagnet and ferroelastic material coupling together, you have piezomagnetic and magnetomechanical coupling. If you have a ferromagnetic and a ferroelectric material coupled together, you have magnetostrictive and piezoelectric coupling. So now please understand this particular plot which is shown over here. If you see, so what you have is you have magnetically polarizable materials, and then you have electrically polarizable materials, out of which few of them are ferromagnetic, and here you have few of them which are ferroelectric. Now the intersection of them, what you have over here is something where you have a magnetoelectric effect, where basically it can be a magnetically polarizable material as well as an electrically polarizable material. It can be ferromagnetic and ferroelastic. Multiferroic is the one which is basically a total coupling between the ferromagnetic and the ferroelectric material. So this is known as, so whenever the materials show these properties and it lies in this particular intersection, this is known as a multiferroic material. So multiferroics are materials which possess more than one type of primary ferroic order in the single phase. So they are either the rare earth magnetites or ferrites or transition metal perovskite oxides. Examples are this TbMnO3, you can have TbMn2O5, you can have holmium manganate as HOMn2O5, lutetium ferrite LuFe2O4. You can have bismuth ferrite, is one of the most well-known example of multiferroic materials, bismuth manganite. Some non-oxides are also multiferroics, like you can have barium nickel fluoride and spinel chalcogenides like ZnCr2Ac4. So these are all these different kinds of multiferroic materials. So a material which has the coexistence of long-range ferroic orders and strong coupling between the pertinent ordered parameters, such as composites which are based on magnetic materials as well as piezoelectric materials. So you can have additional control to input and store data, and these applications are in sensors, in multi-state memories, in actuators, device applications, as well as in biomedical fields. Bismuth ferrite is one of the prime examples, as I said, because in a single phase materials which exhibits magnetoelectric coupling at room temperature. So now there are two types of this multiferroics material. One is type 1 and the other is type 2. What is type 1? It is single phase multiferroics, as in case of BiFeO3, in which both magnetic and electric phases coexist within the same compound, but they have different microscopic origins and they are broadly independent of each other. In case of type 2, what is happening? The single phase multiferroics are materials in which ferroelectric order is induced by magnetism, which in turn suggests a very strong magnetoelectric coupling. So what you are having in type 1 material, you are having basically these different, you are having, when you're having a type 1, both magnetic and electric phase, they are coexisting within the same compound, but their microscopic origin is very different and they are independent of each other. In case of type 2, what you're having, ferroelectric order you will get when you are changing the magnetic field, whereas or the vice versa, and this suggests there's going to be a very strong magnetoelectric coupling. Okay. So what is domains and domain walls in this type 1 and type 2 multiferroics? Let's look into type 1 multiferroic. The magnetic and the electric order, they are emerging independently. So the respective domain patterns do not have to coincide, and domain walls are either magnetic, which you see over here is blue, or electric, which in this case is red in nature. If the domain patterns coincide, a multiferroic domain wall is formed. As you can see over here, this orange domain wall, this is a multiferroic wall. The formation of the multiferroic domain wall points to a coupling between the magnetic and the electric order, which however is not required by symmetry. So this is in case of a type 1. Now in type 2, what is happening? The magnetic order induces electric order. So the ferroelectricity emerges jointly with a magnetic phase transition. Because of the interdependence of this electric and magnetic order parameter, all ferroelectric domain walls are also magnetic domain walls and therefore multiferroic. Ferroelectric, ferromagnetic, magnetic order, multiferroic, ferroelectric order. As you can see over here, all of this is shown in this particular crystal. So all of these are multiferroic walls because here ferroelectricity emerges jointly with a magnetic phase transition. So you have how the domain and the domain walls look in case of a type 1 and a type 2 multiferroic. Apart from this, you can have composite multiferroics. Because why? You have very less amount of single phase multiferroic materials which are operating at room temperature. Many of this multiferroic nature you will find which is operating not at room temperature but at very, very low temperature. And if a material is showing multiferrocity at a very low temperature, then its application is really very, very restricted. And also the magnetoelectric coupling which you see is also very low. So whenever you're looking for applications, you have to look for materials which is going to show multiferroic nature at room temperature, and also this coupling is going to be very strong. So what is the solution to it? So you can develop these multiferroic composite materials. So these are composites these are compounds in which the electric, magnetic and piezo order states coexist within the material. But unlike a single phase multiferroics, which are homogeneous compounds, and chemically isotropic, these composite multiferroics, they are characterized by the fact that the order phases, they are kind of physically separated from each other within the composite material. So these resulting magnetoelectric coupling in these particular materials can be almost 108 times larger than in case of a single phase multiferroic. However, it is observed only at microwave frequency and in a very limited range of operating conditions. So you must understand what are the conditions to see this kind of strong multiferroic effect in composite. So the two individual phases should be in equilibrium. Mismatch between the grain size should not be present. The magnitude of the magnetostriction coefficient of the piezomagnetic or the magnetostrictive phase and the magnitude of piezoelectric coefficient of the piezoelectric phase must be very high. The accumulated charge must not leak through the piezomagnetic or the magnetostrictive phases, and the strategy for polling of the composites must also be determined. So if you look into various application of these kind of ferroic materials, it is applied in memory devices, in sensors, in transducers, in mechanical shifters. You can also use it in wave filters, in displays, in amplifiers, in transformers. So these are the various applications whatever you have in case of multiferroic materials. So one of the application is in the AC/DC magnetic field sensors. So magnetic sensors, what are they? They are devices which can detect without physical contact the creation or variation in magnetic fields of the surrounding environment. And from these changes, they derive information on the properties of the magnetic field itself, as well as indirect properties of other entities such as direction, presence, rotation, angle, speed, electric currents, temperature, and so on. So what you have over here is a magnetoelectric voltage coupling coefficient. So this value is given by this particular equation. Here this T is the thickness of this ferroelectric layer in case of laminates, or thickness of the sample in case of a single phase composite. H is what? It is the amplitude of the magnetic field under measurement, and V is the voltage response of the multiferroic sensor. So a linear response is critical requirement in order to operate this kind of a sensor. So coupling measured at intermediate angles between the 0 to your 180 degree, it shows almost a linear variation, as you can see over here, of the sensor's response. And this indicates possibility of utilizing multiferroic sensors for direct detection as well as for compass applications. Then you can also have multiferroic random access memory and multi-state memories. So we spoke about FRAM. So when magnetic order and electric polarization, these are simultaneously displayed, a multiferroic element could essentially combine the advantages of this ferroelectric RAM and the magnetic RAM to form a non-volatile random access memory with multiple memory states. So two binary states could be encoded by the ferroelectric polarization state, and by integrating this multiferroic within a magnetoresistive multilayer, two additional binary states could be encoded in the resistance state of the multilayer stack. So basically what you are doing, instead of having two level, you are having now four level. So you have strain mediated magnetoelectric coupling in multiferroids. This is utilized to achieve the magnetization rotation of the free layer. So this multiferroic RAM could operate as an all-electric read-write four-state memory RAM, offering less power consumption, more memory density, and non-volatility simultaneously. So you are combining the advantage of a ferroelectric RAM along with that of a magnetic RAM, and you are forming a non-volatile random access memory with multiple memory states. So the greatest application of this multiferroic materials can be in developing this kind of MF RAM kind of materials. So with this, we come to an end with the magnetic materials. If there is any question, you can ask. Kindly go through the slides, and in case you have any doubts, you can anyway reach up to me. I have shared my email ID. So if you have any doubts in this particular, I can understand it's a lot of material, but everything is given. And if you have any further doubts in it, by reading the slides, I'm always available. So please, if you have any questions, you can write an email to me. If there are no further questions, then we end the class here. Thank you.